So this lecture covers this concept of oxidation reduction reactions. So before we talk about oxidation, so a new type of chemical reaction. So before we talk about that though, we have to cover this concept of oxidation numbers. Okay, so oxidation number is basically, it can be just the actual charge on an atom if it exists as a monoatomic ion. So that would be something like NaCl is really Na plus and Cl minus. And so the +1 and -1 is its charge, but it's also its oxidation number. So sodium has a +1 oxidation number and Cl has a -1 oxidation number. Or it could be a hypothetical charge assigned to an atom using the rules. So it could be a hypothetical charge to an atom that's assigned based on the rules below. So as you can see, we have 6 rules here to go through. So meaning hypothetical charge would mean like if we had CO2. Then if we go through these rules, what we're going to see is oxygen is -2 and carbon is +4 would be its oxidation numbers. So one thing that you don't want to do in this chapter is you don't want to confuse oxidation numbers with formal charge. So for CO2, the formal charge on oxygen is 0, 0, and 0. If you remember how to do formal charge, if we took carbon, for example, 4 valence minus 4 lines minus 0 dots. Right, 4 valence minus 4 bonds, 4 lines, minus 0 dots or 0 non-bonded electrons. So carbon has a 0 formal charge, and oxygen 6 valence minus 4 dots minus 2 lines, 0. So carbon, oxygen, and oxygen has no formal charge, but that is a different concept than oxidation number. So oxidation number, carbon's +4, oxygen's -2, oxygen's -2. And that's based on these 6 rules. Okay, so let's go through the rules. So all elements in their pure form, in their pure elemental state, have an oxidation number of 0. So that would be, for example, if you find iron in nature. How do you find iron? You find it as a solid. So if you found a block of pure iron in nature, it would have it's assigned an oxidation number of 0. How do you find copper in nature? As a solid. So pure copper has an oxidation number of 0. How do you find hydrogen in nature? Hydrogen exists as a diatomic molecule, so pure hydrogen would have oxidation number of 0. So some of these are easy, some of these are not some of these are harder to figure out because you may not know enough chemistry to know what is the elemental form of a particular element. Basically, if it's pure, if it's the element not attached to anything else, it's going to have an oxidation number of 0. So how do you find nitrogen in nature? Nitrogen's a diatomic gas, N2. So if it's pure nitrogen, not attached to anything else, has an oxidation number of 0. Okay, so the oxidation number of an atom in a monoatomic ion is the charge on the ion, and we looked at an example of that, like sodium chloride is really Na +1 and Cl -1. So that's their oxidation number, +1, -1. Or if we had something like calcium sulfide. So way back in chapter 2, you know what the charge on calcium is, right? It's calcium 2+, and sulfur is 2-. So that would also be their oxidation number, +2 and -2. Okay, so oxidation number of oxygen is always -2, right? Unless 2 exceptions. If it's O2, then it's 0 because that's pure oxygen. Or if it's H2O2, then oxygen is -1, right? So if it's H2O2, it's just peroxide. Peroxide looks like that. Well, then oxygen is -1. Each oxygen's -1 and each hydrogen's +1. So if you notice, the sum of oxidation numbers in these cases equals 0. So, but in any other compound, oxygen is -2. right? So if it's lithium oxide. So this is something that we've kind of been doing throughout the semester already. So you know that oxygen likes to be -2 charge, because if it gains 2 electrons, it looks like neon. And you know that lithium likes to be +1 charge. If it loses 1 electron, it looks like helium. Well, that is also their oxidation numbers. So lithium would be +1, oxygen -2. Or if it's an H2O, oxygen's -2, hydrogen's +1. Okay, so the next rule applies to hydrogen. So oxidation number of hydrogen is always +1, unless it's H2, in which case that's pure hydrogen, so it's 0. Or if hydrogen is bonded to a metal, then hydrogen is -1. So if we take some examples, so HCl, NaH, what else could we do? Let's see. We did H2O. So could be LiH. So in these cases, what's the oxidation numbers of hydrogen? Okay, so HCl, hydrogen's +1, Cl is -1. But if it's NaH, then sodium is +1. In this case, hydrogen is -1. So one HCl is hydrogen +1, but an NaH, hydrogen is -1. And this relates to electronegativity. Right, so chlorine is more electronegative than hydrogen, so chlorine gets to be the one that's negative, and that makes hydrogen positive. But in this case, hydrogen is more electronegative than sodium. So sodium gets, so if, since hydrogen is more electronegative, it gets to be negative, and then sodium is positive. So in H2O, oxygen is -2. That's rule 3 above. Oxygen is always -2, unless it's O2 or H2O2. So if oxygen is -2, then hydrogen has to be +1. And of course, the sum of oxidation numbers, so there's 2 hydrogens, so that would be +2. And then the sum of the oxidation numbers, since this compound doesn't have to have charge, has to sum to 0. Okay, and lithium hydride, so lithium would be +1, hydrogen -1. Again, since hydrogen's attached to a metal, it's -1. Okay, fifth rule applies to halogens. So halogens are always -1. That's something that you kind of already knew, right? Because fluorine gains 1 electron, it looks like neon. If chlorine gains 1 electron, it looks like argon. Right, the halogens are the group 7. They like to gain 1 electron to look like the noble gas. So halogens are always -1 unless they are attached to another halogen. Or they're attached to themselves. Like F2, then it's 0. Cl2 would be 0. Br2 would be 0, since that's the pure form of the element. But if it's attached to another halogen, like ClF, or bromine attached to iodide, well, now they both can't be negative, because the sum has to equal 0. So if it's Cl attached to fluorine, then fluorine gets to be negative and chlorine gets to be positive. So why does fluorine get to be negative? Because it's more electronegative than chlorine. And if bromine is attached to iodide, then bromine gets to be negative, and that means iodide has to be positive. Because bromine is above iodide in the periodic table, so it's more electronegative than iodide. But in other instances, if it's attached to something else like hydrogen, then the halogen is negative. And then the 6th rule, if it's a polyatomic ion, so like NO3, -1, Right, so then that's the net charge, -1. So in this case, the sum of oxidation numbers on the nitrogen and the 3 oxygens has to total -1. Okay, so what's the oxidation numbers on everything? Well, so oxygen is -2, right? That's rule 3. Oxygen is always -2 unless it's O2 or H2O2, and that's not H2, and that's not O2 or H2O2, it's NO3. So each oxygen is -2. So that would be 6 negatives. So then what does nitrogen have to be? Well, the sum has to equal -1. So nitrogen must be +5. Right, that would be 6 negatives, and +5 would equal -1. Sum of oxidation numbers has to equal the charge on the polyatomic ion. And again, don't confuse. So don't confuse oxidation number with formal charge. Right, if we calculate formal charge on nitrogens and oxygens, this oxygen's 0, this one's -1, and this one's -1, and then nitrogen is +1. So if you sum formal charges up, the sum of formal charges equals the net charge, but so does the sum of oxidation numbers. So if you sum this up, 6 negatives and +5, then you get -1. But they're two totally different concepts, right? Formal charges is valence minus dots, right? Minus the non-bonded electrons, minus lines. Whereas oxidation number is based on these rules that you just have to know. Okay, so let's take a few more examples. So KMNO4, Ca3N2, let's take MgNO2. So if we assign the oxidation numbers for each of these, NH4COO4, CO3PO4, 2. So every single element in a compound gets an oxidation number. And to do oxidation numbers, you have to know the charges on the polyatomic ions, right? For example, you have to know that NO3 is -1. If you don't know that, you can't do this. So if you don't remember your polyatomic ions, you got to review them and make sure you know that what their charges are. So for this KMNO4, so what's the oxidation numbers of everything? Where to start? We'll start with oxygen, because oxygen is always -2, right? So that would be, since there's 4 oxygens, that would be 8 negatives. So potassium and manganese have to balance that to 0. Well, you know that, so permanganate is one of the polyatomic ions that you have to know. So what's the charge on permanganate? Its net charge is -1. So if oxygen is -2, and that's 8 negatives, then what does manganese have to be so that the sum is -1? Then manganese must be +7. And then they sum to -1. So manganese is +7. And then, so the sum on KMNO4 is 0, right? There's no charge. If there was a net charge, it would have to be shown. So that there's nothing shown, then you know it's 0. So if each oxygen is -2, that's 8 negatives, and manganese is +7, then potassium has to be +1. So the oxidation number is potassium is +1, manganese is +7, each oxygen is -2. So I don't want the sum of oxidation numbers for each element. I want what each element's individual oxidation number is. Okay, so for Ca3, N2, so some of these, so this is not a polyatomic ion, so this one's easier to figure out. So you just have to know that nitrogen likes to be -3 charged, right? Because of where it's at in the periodic table. And then calcium likes to be +2. And the sum of those oxidation numbers is 0. So that would be 6 negatives, and that would be 6 positives. So each calcium is +2, and each nitrogen is -3 would be its oxidation numbers. Okay, so for Mg, NO2. Okay, so NO2 is again a polyatomic ion. To do this, you have to know its net charge. Its net charge is -1. So nitrogen and 2 oxygens has to equal -1. So how to solve this? Again, oxygen is always -2, so easiest to start with oxygen, so that's 4 negatives. And the sum has to be -1. So that means nitrogen must be +3 since there's only 1 nitrogen. So 4 negative, 3 positive is -1. So oxygen, so nitrogen's +3. Each oxygen is -2. So that would give you, since there's 2 nitrogens in the compound, that would give you 6 positives, right? There's two NO2s, so 2 nitrogens, that would be 6 positives. And that would be, so -4 from the 2 oxygens, but there's 2 of them, so that would be 8 negative. And so that would mean, and this has to sum to 0 since MgNO2 has no net charge, so that means magnesium must be +2. So magnesium, that'd be magnesium nitrite, right? NO2's nitrite. Okay, so for NH4ClO, ClO4, so again, you have to know, so these are polyatomic ions. So you have to know that NH4 has a +1 charge. And you have to know that ClO4 has a net -1 charge. Again, if you don't know that, you can't do this part of the chapter. Okay, so for oxidation numbers, hydrogen's +1, so that would be 4 positives. And it has to sum to +1, so then nitrogen must be -3. So -3, that's +4. And so for ClO4, oxygen's -2, so there's 4 oxygens, so that's 8 negatives total. Has to sum to -1, so that means chlorine must be +7. So +7, 8 negative would sum to -1. So chlorine's +7, oxygen's -2, so that's +7, that's 8 negatives, and if you sum all of that up, that equals 0. So if you remember, what's the name of NH4ClO? NH4 plus is ammonium, and ClO4 is perchlorate. Okay, let's see. One more, CO3PO4. Okay, so PO4, again, you have to know the net charge or you can't do this. So the net charge on PO4 is -3, right? That's phosphate. So start with oxygen, it's -2, so that gives you 8 negatives. And then whatever phosphorus is plus the 8 negatives has to give you -3, so that means phosphorus must be +5. So +5 8 minus gives you -3, so phosphorus is +5. And now you can figure out the cobalt. So the easiest way to figure out the cobalt, so PO4 as a whole is -3, and there's 2 of them. So that gives you 6 negatives. And the cobalt must balance the 6 negatives to 0. So since there's 3 cobalts, then each cobalt is +2. So that's +2. We said phosphorus was +5, oxygen's -2, and these all should sum to 0. So that's 6 positives from the cobalt, from all cobalts. There's 2 phosphorus, so that's +10. So there's 4 oxygens, each one's -2, so that's 8 negatives, but there's 2 phosphates, so that's 16. That's -16 from 8 oxygen, and that all sums to 0. But you kind of already knew this back at chapter 2 when you had to name chemical compounds. So what's the name of this if you had to name it? It's not just cobalt phosphate, right? It's cobalt 2 phosphate. Right, the Roman numeral in the transition metal's name is its oxidation number. Okay, we'll take 2 more examples. Something a little harder, something a little bit easier. What would be an easy one? Let's see. Not that. Cesium oxide. Okay, so this one's easy because it's so CS2O is easy because it's not a polyatomic ion. So oxygen's -2, and cesium, there's 2 cesiums, each one must be +2, +1. That gives you 2 positives to balance this to 0. But you could figure this part out just from the periodic table because cesium's a group 1 metal, and you know group 1 metals like to be +1, right? Group metals, 2 metals like to be +2. The ones that are harder are the polyatomic ions because you have to know their charge. So ClO has a net -1 charge. So each oxygen's -2, so that means chlorine must be +2. No, it means chlorine must be +1. So that way they can sum to -1. So chlorine's +1, oxygen's -2. What's calcium? Well, since there's 2 of these, that would be there's 2 negatives that must be balanced to 0 by calcium. So calcium would have to be +2. So again, so calcium plus, so that's 2 positives from calcium. Each chlorine's +1, so that's 2 positives from all of the chlorines together. And then each oxygen's -2, and there's 2 oxygens, so that's 4 oxygens, 4 negatives from all of the oxygens, and that sums to 0. But if I ask you what the oxidation numbers are, calcium's +2, each chlorine is +1, each oxygen's -2, so I just want the individual oxidation number for one single element, one single atom of the element, not the sum of the oxidation numbers for each element. Okay, hopefully that made sense.